Well, so far what we have done is we have talked about acceptors and donors. Okay. So we can dope with acceptors and donors, but in reality, most often what we do is we have both donor and acceptor impurities in a semiconductor. And such a semiconductor, we call it as a compensated semiconductor. Why would we do that? Well, for example, take a semiconductor. Let's say it has a no. Generally, we don't work with intrinsic semiconductors. We have a starting doping. Let's say background doping of Na. Okay, we have a p-type semiconductor. Okay, we have a p-type semiconductor initially. Okay, just a block. I'm just representing now because I want to make. I need both n-type and p-type devices. Okay, we can't work with only one of them. It's we could do something, but it's not going to be very helpful. Okay? It's essentially a piece of resistor, you could say, right? Only one type of carrier is there, nothing much. I mean, it will have some resistivity, but nothing much interesting happens. But if you combine both n-type and p-type, then a lot of interesting things can be done. So I take this initial piece of p-type semiconductor and I want to make it n-type. How would I do that? So what does it mean if you have a piece of semiconductor which is, uh, so if I plot uh, the density, I mean, essentially you started with Na, right? Then what I'll do is, if I want to make it, some part of it, I want to make it n-type. Let's say I want to make this part of it n-type. What would I do? I simply, dope it with higher amount of Nd. So half of it I'll mask. This I will mask. I will not expose it, and then I'll only dope only one particular region where I want the concentration to be n-type. Okay, this is what we regularly do. So this is a very important thing. What happens to carrier densities in a compensated semiconductor? Okay, this is an important thing that you might have to regularly use to calculate. Okay, so to do that, we use what is known as charge neutrality relationship, by which what we mean is initially your dopant is charge neutral, silicon lattice is charge neutral, right? When we put in these charges, again the charge neutrality has to remain, right? So whenever we add a donor, we said that donor gives an electron, so electron is negatively charged, so donor atom becomes positively charged. So I'll simply represent that. So basically you have Nd, and just to say that it is positive, I'm putting a superscript positive, and you are introducing an electron into the lattice which is negatively charged. So I'll put a minus n, which is represented, or I'll take it equilibrium concentration, so minus n naught. Okay. Now this is with the donor impurities. What happens with the acceptor impurities? Acceptor impurities are those that are accepting electrons from the lattice, so they are becoming negatively charged. So an acceptor impurity, I'll put a minus sign and minus, and then it is creating a hole in the lattice, which is essentially a vacancy of an electron. A lack of an electron is called as a hole. So I'll say it is P naught. Now, because we are starting with uncharged dopants and neutral dopants and silicon lattice, this total has to remain zero. All right. So we also said since it's an equilibrium, we know that this guy is going to be Ni square by Nd. I'm assuming that, okay, assume this is only analysis for assume Nd is greater than Na. Okay. So majority carriers are electrons. I'm assuming that it is inherently. So if I do this, so I can put Np equal to P naught equal to Ni square by N naught. Okay. Then I can just play around with these numbers. So what I will do is I'll drop the I'll drop the positive and negative. Just I'll simply write it as Nd minus Na. Okay. And then I'll take the Ni square to the other side. So I can write this as, and then I multiply. So this is it kind of looks weird, but this is N naught. Okay. By N naught. Okay. So this I will write it as N naught minus N naught square equal to minus Ni square. Right, that's what it should be. Okay. All right. If I do this, I'll rearrange terms. So I'll say N naught square. I'll take it the other side so that it's positive, minus Nd minus Na times N naught. Again, I'll leave it minus Ni square equal to 0. So essentially what we're seeing is your carrier density is a quadratic equation. So you could simply write out the solutions. Okay. So N naught is going to be, ND by ND minus NA minus B plus. Okay, we will only take the positive root. Okay, we will see in a moment why we take only the positive root. So if you take the negative root, then at some point the carrier concentration might be 0, which we can't have. Okay. Square root of ND minus NA whole square minus, oh, it should be plus. It's minus 4AC, right? Plus 4 into A into C. So then, okay, Ni square by 2. Okay, so I can rearrange the terms, and finally you can write this as ND minus NA divided by 2 plus square root of ND minus NA divided by 2 whole square plus Ni square. Okay, so this is your carrier concentration for a case where you have a compensated semiconductor with ND greater than Na. And if I have Na greater than ND, I will not, prove it, but I will write, well, yeah, Na greater than Nd, then P naught is going to be equal to Na minus Nd divided by 2 plus square root of Na minus Nd divided by 2 whole square plus Ni square. You could verify it. Okay? It will work out to be correct. So, well, this is your majority carrier concentration, and the corresponding minority carrier concentration will be simply Ni square divided by whatever is the majority carrier concentration. All right. So this is an important relation that we come across. Let's take an example and try to solve it. Okay. So let's see. So we have a problem here. This is from example problem. Please go back and verify that if you want to make sure that you get it right. So what I'm asking is here, determine the thermal equilibrium electron and hole concentrations in silicon at T equal to 300. Okay, it's only at a certain temperature. And given that there are some doping, Nd, let's take the case 1, Nd equal to 10 power 16, I'm not writing the units, Na equal to 0. If your Nd is 10 power 16 and Na is 0, so basically this goes to 0, this goes to 0, and so you have essentially Nd by 2 plus square root of Nd by 2 whole square plus Ni square. And remember, this Ni square is going to be quite small. It's 1.5 into 10 power 10 compared to Nd, which is 10 power 16, right? This is going to be 10 power 16. So you can neglect the Ni square. So this will be almost equal to Nd. So basically we got back whatever we had the situation, right? Whenever you had only donor atoms, we said the electron concentration is simply going to be Nd. And then what will be the whole concentration? P naught is going to be Ni square divided by Nd. This is the whole concentration for the part A. But part B, what we are saying is we are given that Nd, sorry, should be written as Nd equal to 10 power 16. Oh, well, no, it's different number. Nd equal to 5 into 10 power 15 and A equal to 2 into 10 power 15. Okay. So, well, you have acceptors and donors. So now you can try to calculate it. So it should be Nd minus Na. So Nd minus Na would be 3 into 10 power 15 divided by 2 plus square root of 3 into 10 power 15 divided by 2 whole square plus Ni square. Well, again, we can neglect this. So this will approximately be equal to 3 into 10 power 15. So this is a naught. So P naught is going to be Ni square divided by 3 into 10 power 15. All right. Of course, sorry, I should actually, in the previous case, you should be careful. This I should not say is N naught. Nd, I should call it N naught. So that, because, yeah. All right. So you get the drift over here. So please, make sure that you verify this thing. See what happens as you adopt different carrier densities, okay? And always remember this relation, which we N naught P naught equal to Ni square. Whenever you have thermal equilibrium, at thermal equilibrium. In the next week, I'll talk a little bit more about what is equilibrium, steady state, and so on. We'll come to it in a little bit more detail. But for now, we saw that there are these two processes, And whenever they are in equilibrium, we call it n not into p not equal to ni square.